המעבדות שהם ניסו, כן, ניסחתי, פשוט ישבתי וניסיתי פרמטרים וזה, עד שיצא לי טוב, וכתבתי. זה עוד לא קרה, אבל זה כאילו, זה לא יהיה הגיוני מבחינת השעות. זה שבור, כאילו.
היו שניים.
8 שעות.
לא, היה אחד שהיו בו 10 שעות.
לעשות את זה מאוחר, לנגנים זה כאילו, זה לא בא בחשבון. כי לפחות בעצם המעבדה היא באמצע ניסים. אתה רוצה לעשות את זה? בניסים נגרר מאוד מאוחר.
טיפונת פחות מהשניים עוד שעות.
לא, כן, ניסים שלנו מגיעים ב-8-9
נכון, כן, אם זה נתון
ניסוי שלי יש 8 שעות מינימום.
סיכויים...
עכשיו אני נתן שני הספרים, כל אחד זה 3 שעות רק על הלמידה, וזה בלי כל הסשנים שאני כן עושה אימג'ינג, וכל הלסדר. זה הגיע ל8 שעות ובלי שנפתחו לי דברים. לא, זה לא בזה. זה סתם קומפוזות. יכול להתחמש בכל מיני דרכים. זה ממש בקרוב, זה לא מסתכלים.
האמת אני צריכה להגיד לו, קל לי שפשוט לעבוד עם ניסים של הכל מעניין אותו, אני
זה כאילו, מוזר כמה טריוויאלי ולא ידוע, כאילו לא ידוע מה זה באותו זמן. מה ההסבר לזה שגם מקדם חלקי וגם מקדם
הוא לא יודע, זה הכל שקר,
זה כאילו,
זה הכל
זה
פיקציה,
פלסטרים,
הם לא
נכון?
קבועים בכלל, אין דבר כזה, שם את זה מישהו, שנים הוא הכל ניסוי כל החומרים וקבע
אבל זה תלוי במהירות בעצם, באופן בסיס?
כן, זה משהו...
גם חיכוך אוויר תלוי במהירות, נכון? בעיקר שהנוירון הכל זה את כל הכסף. סבבה שהתפקיד של הבניין הוא הרבה מאוד
כאילו, אבל זה צריך גם להשאיר. כל תורם
זה לא נטו מה שדעת.
יש מין הסכם כזה, כן. נכון.
מה, אם הם הסבירו שם?
אני לא יודעת מהחברות הם הסגירו, אבל יש...
תמיד הברייתא
וואי, זה הופך את הביקורת להרבה יותר מוצדקת.
הם צריכים להיות כריזמטיים יותר.
שאלות היו ממש אתה להניח חנטר, מה?
אבל אין לו כל כך הרבה... יש
לא, עכשיו אנחנו לומדים משהו בלילה.
היה כזה איליה, קטנה. נראה לי יותר כאילו הרבה יותר לבן שרון.
בחדר שלו בטוח. זה זורק טילים משלמים כאילו כמו שאסף היה.
יש משחק שם פתוח?
הוא היה במחזור שלי, לא יודע איפה שנה מה, כנראה שהוא לא היה במחזור שלי, כנראה שעשינו בקצה הקורס הזה. הייתי בטוח שהוא במחזור שלי, ואז פתאום כשהייתי בשנה שלישית, אז הוא כבר היה במחזור.
Yeah. אני כל זה בייתי
פיזיקה הוא טוב.
Okay. Good afternoon. I apologize for the late start. So, we're going to continue talking about the linear perceptron. Most of it you've gone through with Neta, but I'll remind you of some of the main things that you derived, and a few more things. And then we will move on to another type of learning. Thanks for reminding me. So, I understand that in the previous course, in Reshatot Aleph, each time someone prepared a note, right? So we decided to do the same thing. Is anyone volunteering to do it today? Okay, we'll decide. I'm not going to pick. Okay, you asked to.
Can I do the previous lesson?
Sure, definitely.
Can I do today? Okay, sorry. I thought that was a previous question.
So each lecture, someone will, if you want, someone will prepare lecture notes. We, meaning Neta and myself, probably Neta, will go over it to see that it looks okay, but we cannot guarantee that it's, so this is an important point to make. We're not guaranteeing that everything written in the notes is correct. Okay? It's your responsibility, everyone's responsibility to also take notes or do whatever you need to make sure that you follow the lecture. And you will receive, I think, 3 points for the course, bonus for the course. I mean, anyone who will submit, you can do it once. I mean, you can do it more than once, but you will receive credit once. You will receive a credit.
So this is like completely something about the notes generally.
Yes.
I heard that last year some people, when they wrote the notes, they extended a little bit more about what was
Yes.
happened in class. Sometimes we jump, and for
Yes.
me, not all the jumps are trivial.
Yeah.
And then if somebody just takes the time and go over it, and you can see all the steps, it really helps for the test. So I would like to request that if you can make sure that like if each one of us does one lesson very well, then we will all have like a really good one.
Yeah, and one other thing that you can do maybe is post comments. So if you see something in the notes that you want to comment on that you think might be useful for other people, probably the way to do it is on the discussion forum on the Moodle. Yeah.
Yeah, because I think what like copying is exactly what we had discussed, but not enough to.
Yeah. So I mean, it's obviously just writing the notes, just the equations that are written on the whiteboard is not enough. Obviously, I'm saying a lot of things during the lecture, and you want to create out of it something which can be really followed. All right. So we started to discuss some theory of supervised learning, and we discussed the linear perceptron. So the architecture of the linear perceptron is very simple. We have some input units, which are, for each example, we can describe them by a vector. And all these, the values of these input units are summed out by the output unit linearly with some weights. And the idea is that what we want this output unit to do is to approximate some function f of x. And the way it works is that we observe some examples. So the examples will be x mu, y mu, where mu goes from 1 to p, p is the number of examples. And we're trying to train this network, actually just one output unit, to approximate the function based on these examples. And the approach that I think I put, now I see that I put the mu in the superscript, so I will do it like this here as well. And the approach that we took was to take these examples, which we call the training examples, and to find a set of weights that minimizes the training error. So the training error, so maybe the goal is to approximate this f of x, and the approach is to minimize the training error, which we define as, is this still okay? I never know about here, I don't know. No, it's not okay. So, so let's see. So the approach was to minimize the training error, which is, we define it as 1 over p sum over mu w transpose x mu minus y mu Okay, so it's a square, sum of square errors. All right, and then we started to ask ourselves what does that actually mean? What is it? What is the W that minimizes the training error? And the important distinction that came up is that things look different if the number of examples is larger than n or smaller than n. So what you saw is that when p is at least as large as n, for typical examples, unless the examples are very special, this training error has one minimum. There's one W that minimizes the training error. And so if we would plot the training error, I'm doing it a bit schematically, as a function of the weights, then it's some multidimensional paraboloid. It's a quadratic function, which is, just a second, which in all directions is convex. So then it has one minimum. Yes?
You put on the mic?
Oh, yeah. Thanks for reminding me. Is it because you can't hear me?
No,
or
because
just
if
whether
you button the
yeah.
video, then
Yeah.
you don't really hear it.
Yeah. All right. So and maybe I will write down also the solution. The optimal weight, which I denoted in this way, which is the weight that minimizes the training error for the training examples, is some matrix. And I wrote expressions for we wrote expressions for these matrices. In a few minutes, I will write what is C again, just to make out some points. So I will not write it again right now. And so this is the case where P is larger than n. Now, when P is smaller than n, when you actually, if you just try to do the same thing that we did when we try to do it for P larger than n and write what is this matrix C, and we try to invert it, we see that it's not invertible. So we cannot write the solution in this way, but the reason is that actually there are many, it's not that there's no solution, there are many, many solutions. So in this case, so for P smaller than n, C is always singular, non-invertible. And the training error can be set to be 0. Okay, so it's possible to realize exactly this function on all the examples. And for many choices of the weights, and you can write the choices of the weights in the following way. I hope that I'm using the same notation that Netta used. So the weights that you can write can be written as a sum over the examples. Over the examples mu, omega mu, x mu. So x mu are the vectors of the examples. Plus something that I write as the orthogonal part. So before I need to tell you two things. What are these omegas? Okay, we'll write them in a moment. And what I mean by this. So this is any weight vector which is orthogonal to all the examples. So and if P is smaller than n, then there's always, this spans a space which has dimensions larger than, at least as large as 1. And so there are an infinite possible ways to choose the weight such that they exactly realize the function. And the omega mu's can be written as, I will write it, can be written as a matrix product, but I want to write it with the indices explicitly, because just not to confuse with what we did here, because here the vectors are, what is the dimension of these vectors? N, right? Now here I'm running over the indexes of the example, so what I will write here is some matrix which is P by P. It's not N by N as we had here, and here it's the inverse of this matrix, and mu goes from 1 to P. So we could have written it also as here, as a matrix, inverse matrix times a vector, but now the vectors and the matrices are p-dimensional, the number of examples. And Q is Q mu nu is the scalar product of the vector x mu and x nu. Okay, so this you did with Netta, right? Yes. Okay, so just before we continue, I want to highlight just on a very technical level that these two situations are very different, but technically there is some similarity between what is written here and what is written here. And to do that, I would just want to write down Q, the matrix C. So the matrix C I didn't yet write. So C training ij it was 1 over P sum over mu xi mu xj mu. And the matrix Q I will write again, Q mu nu is a sum over I going from, so mu goes from 1 to P, and Q is a sum over I going from 1 to N of x I mu x I nu. So you see that this is like a correlation function of x, the entries of the vector x, I and j over the examples, the empirical correlation of I and j over the examples. And this is like the correlation between x, the ith entry of x over, the correlation between the ith entry of x between the muth example and the new example. So summed over all the indices I. So it's like, so there is some similarity. Here we sum over I, here we sum over mu. Anyway, but this is a P by P matrix, and this is an N by N matrix. All right. So I think by here this is more or less where you probably stopped with Netta, right? Okay. So now I want to introduce just a definition, and the definition is the following: a realizable pattern a pattern is just a set of examples, okay? And the realizable pattern is one such that there exists some W, let's call it W0 exists, such that the desired function is evaluated exactly. Okay, so in other words, y mu is equal to W transpose x mu for all mu. And another way to write this is that the training error is 0. So this is just a definition, and it's just another, using this definition we can say what we said before in slightly different words. So for P smaller than n, any pattern is realizable. And for P larger than n, then usually not. That E training is larger than 0. But we can easily think about some examples where it is true. So, for example, it depends on the function. If, for example, if this function is a linear function, if the function that we want to approximate is a linear function, for example, if f of x is some w tilde transpose x, then of course in any dimensionality every pattern will be realizable, and we can just choose if we choose w 0 equals w tilde, then we will get E training error equals 0. And it's actually a nice exercise to take what we developed here, which is a general way to minimize the training error, and write the weights in this way, and check that if actually the function that we are approximating is a linear function, we're going to recover that function by doing this, okay? It's a nice exercise to do. All right, now from the point of view of learning something about the examples, is this a good situation to be in? Yeah, I mean, if every function is realizable, then obviously if we now have another example, so if P is smaller than n, if I give you another example, we could in principle, using this scheme, achieve any value for that next example. So we can hope to really approximate well a function in this situation, not in this situation. We want to have enough examples. Now, therefore, the next thing that we want to discuss is how can we quantify how well we're doing. We're training our weights based on some set of examples. And what we care about really is not the performance on these examples. What do we care about? What? Yes. So what does that mean to generalize? So now we need to go back to the setup that I discussed when we started to talk about learning. Remember that we imagined that our examples are drawn from some distribution, right? Both the training examples, but also next examples that we might encounter when we want to apply this approximation. So once we've defined that distribution, we can define there's a well-defined question, which is how well are we doing on a general example drawn from the set of from the space of examples with the probability distribution that we defined. And this is called the generalization error. So so it's an average error over the examples, and so we can write it. The generalization error is a function of the weights, and we can write it down as the integral dx. It's it's a multi-dimensional integral, okay, because x is n-dimensional. This is the probability distribution from which the x's are drawn. We defined it when we started to talk about learning, about supervised learning. And here we will have the error, our measure of error for that particular examples, which depends on W. So since our measure of error, the measure of error that we adopted here, which I remind you is a choice, the measure of error that we adopted is a quadratic error, then we can write this also as the integral over dx, p of x. This half is just for, we decided to put it in. And so we have our f of x minus w transpose x square. Okay, and often now a general notation that I will use a lot in the course, often when we do these kinds of averages, we denote them by kind of angled brackets. So when I write something like this, what I mean is an average over some distribution. Sometimes I will not write explicitly what is the distribution over which we're averaging, and sometimes just to remind ourselves what we're averaging on, I might write something like this to represent the fact that we're averaging, x is averaged over the distribution p of x. Okay, so this is a definition of the generalization error. And now we want to ask, within this learning scheme that we discussed, where we train the weights to minimize the error, what can we say about the generalization error? Now, in real life, if we suppose that I give you some examples and some set of examples, and you want to estimate the generalization error, what can you do? Yeah, exactly. So this is what we would call cross-validation. You would keep some aside and not touch them, and that would give you some idea of how well you might expect to be doing. There is a price to pay because you're training on a smaller subset, but you get some estimate of your generalization error from the ones that you didn't train on. So now the behavior of the generalization error depends, of course, so the generalization error depends on many things. It depends on the function, the properties of the function that we want to approximate. For example, if the function is a linear function, then we have enough examples, we will find the correct weights, and our generalization error will be 0. If the function is not linear, then we cannot hope our generalization to be 0. But the generalization error depends also on the probability distribution of the examples. So if we have some function which is extremely nonlinear, but all our examples are drawn from some small subspace where it's approximately linear, our generalization error will be small. And the generalization error is also dependent on the specific examples. In each case in which we train our weights, the generalization error depends on the weights that we've seen. So we can, it's not clear that it's possible to say something much about the generalization error, but nevertheless there are some statements that can be made about how it behaves for this linear classifier, for this linear for the linear perceptron, and so what I will draw now is I will not prove what I'm saying. I will just tell you a little bit about how the generalization error behaves. Some elements of what I will write we know, and some I will just tell you. So what I want to draw now is what I would call learning curves. And I will draw two types of error. One is the training error, and one is the generalization error. And I will draw this as a function of the number of examples that we observe. So, what can we say about the training error? One thing which we can say for absolutely for sure. That what? How low? 0. Yeah. So we know that up to n, the training error is 0. So this would be the training error in black, and I will draw another type of error, the generalization error, in a moment. And then it will, when we start to see more examples, then unless some very special things are happening, the training error will increase. Now, what can we say about the generalization error? So let's use another color. So what can we say about the generalization error for p smaller than n? Yeah, but it's even worse. It's even worse. I claim that it's not even defined. It's not defined because we don't have here one possible choice of the weights. So it is defined if we would make some specific choice beyond what we. Okay, it's not written here anymore, but we had there are many possible choices for the weight. So unless we make a choice, it's not defined. So I want to discuss the generalization error for p larger than n, where we have a well-defined choice of the weights. And how do you expect it to behave as we see more and more examples? It will decay, because as we're seeing more and more examples, we're really sampling the probability distribution. If we have an infinite number of examples, then the generalization error becomes identical to the generalization error. The training error becomes identical to the generalization error, right? Because if we have an infinite number of examples, we're really sampling this probability distribution exactly. And then the training error becomes the same as the generalization error. So, and that's what we're optimizing. We're optimizing the training error. We're minimizing the training error. So the generalization error will decay. And what it will decay to is something that I will call E min. And E min is the best possible generalization error that you can get. What is that? It's the generalization error for that particular set of weights that minimizes the generalization error. In other words, I can write it as argmax over W. W, let's see how I denoted it in my notes, just to be consistent. Yeah, just W. Okay. So EG of W. So there is some minimal generalization error possible, and as we see more and more examples, and we minimize the training error, but as we see more and more examples, the generalization error approaches that minimum, and the training error, and we also just discussed the fact that under this situation, the training error and the generalization error are the same. So now we can fill in all those. This line, and this line approaches E min 2. Okay. Arg min. Arg min. Thank you. Arg min. Yeah. It's the minimum. It's the minimum, and W. Right. No. You're absolutely right. So why did I write arg min? because it's the error of some W opt, which is the argmin. So this is just the minimum, or let's write it like this: E minimum. So I was just a bit sloppy. This E minimum is the generalization error of W opt, and W opt is the argmin over W of EG of W. Good. Okay. And so this W opt is really the best possible choice of weights to approximate the function over the probability distribution of the x's, right? Now, I will just want to point out that there are some things that can be said about the behavior of these curves, which I will not show, but for just the way these curves behave for large p. So I will just mention it because it's nice that you can show that. You can show that the training error of p, so that's for, so let me write it here, that's for p going to infinity. When you see more and more examples, the training error behaves like E min minus some constant over p. Now, when I'm writing something like this, and also in the plots that I'm plotting, this is like the average training error over many realizations of the learning. You draw examples, you set up the weights, and you see what is the training error. And so it behaves like this, where A is some constant that depends, of course, on the function that we're trying to approximate and on the probability distribution of the examples. And if you look at the generalization error, it behaves like E minimum plus A over P, and it's the same A in both of these dependencies. A is some constant. It's a constant, and what can it depend on? It can depend on the function that we're trying to approximate, and it can depend on the probability distribution of the examples. And so I just want to highlight some questions that we might want to ask about how well can we do with the linear perceptron, but similar questions can be asked about other architectures. And then maybe we will take a break. So what are some important examples or questions that we can ask about these curves?
When do they reach the minimum?
Yeah, so they are asking something about how fast they reach. So this is, I want to talk about that, but I wanted to list that second. What else? Just in terms of how well we're doing. What is a good? What does it mean, right? So this tells us how well we can approximate the function, in a data case where we see a very large number of examples. Is it small enough? And of course, this depends on the function. It depends on the probability distribution of the examples and on our choice of architecture. The fact we're approximating with some linear. In a linear way. And another question is, so I will say it a little bit different from what you said, in a slightly more general way. Can we find a learning algorithm that will converge quickly. Quickly meaning in terms of the number of examples to E-mean. Now, our learning algorithm is maybe a big word for what we did here, because in this here, well, we have an algorithm. Our algorithm is to calculate a matrix C, invert it, calculate a vector U, multiply C inverse by U. But the reason I'm saying learning algorithm is that often, in many, if we would try to do something more complicated than a linear approximation, we might not have some analytical expression for the best choice of the parameters or the weight. Okay, and then we might need to apply some more complicated scheme in order to find the weights, and that's what I would call the learning algorithm. And so I'm framing this as a more general question that we can apply to additional architectures. Can we find a learning algorithm that will, how fast can we expect to converge? And this will depend sometimes also not only on some general bounds, but also on how we apply, how we try to find the best weights. Okay, so I think that this is a good time to take a break, because I'm going to start another topic. Let's reconvene at 1, okay? So I'm cutting a little bit of the break because of my fault, because of being late. רגע, לא, יש... כן, 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 בבקשה הייתה לפרואקטיבית
פעם ב3 חודשים, שלא. כולנו יודעים. בסדר. מה זה? הוא נראה לי פתרון.
כן, התבלין, תקבלו אותם גם
גם עד סוף הפגישה האחרונה תמיד הכנתי אוכל.
בבקשה לכם להמשיך.
גם בשבועיים.
מה שאני לא זוכר זה כמה זמן אנחנו יכולים לשמוע את היישום של התרגיל עד לפעמים אנחנו, התרגיל כולל גם דברים שהם עוד קצת דורשים עוד חשיבה של ההסכם. אני לא זוכר כמה זמן אנחנו נתנו, ואני אצטרך להיזכר עם נטע.
זה פעם בשבועיים, תרגיל שם פחות ומתי בערך?
עכשיו? כן, בסוף השבוע זה ביום החמישי זה כבר מתרגיל.
תודה רבה. מצוין שאני אתן.
היי.
להגיד שלום.
בואו נפגש איכשהו לדבר קצת. היום אני לא חושב שאני אצליח. אולי בסוף השיעור נלך לבר יוזנה. בסדר?
לראות את זה מהצד פתאום. Funziona forse?
No,
אוקיי. כאילו אתה עכשיו עושה, יש לי אוסף ציוצים כללי, לא. אתה מקבל כאילו תואר ראשון, כאילו, יש לך תואר ראשון במתמטיקה, תואר ראשון.
Okay, so I was asked about the schedule of home exercises. You will get the first exercise this week on Thursday, although there will be no TA session, but you can start working on it. So this Thursday I will teach 2 hours. I don't remember what's your policy when you need to submit it, so this I will update you on Thursday. But in general, you will receive a new exercise every 2 weeks. Okay, so our topic now, so far we discussed functions which are continuous functions. It's a mapping, the functions are a mapping from Rn to R, right? And the next example that we will talk about is very important, and this is the binary perceptron. So let me just first write some title. So this is our topic, but before I describe the binary perceptron, which is a particular architecture, I will describe the concept of a dichotomy. So a dichotomy is some function from Rn to zero or 1. Okay, so how else could we call a dichotomy? I want something more. It's binary, but in terms of what is the task that we're performing? Decision or classification. Okay, so remember that when I started to talk about, say, I introduced the concepts of supervised learning versus unsupervised learning. I talked about the example where I show you many images, and you have to decide whether the image is an image of a cat or a dog. Okay, or maybe you just have to decide whether there is a cat in the image or not. This is an example of a classification, a binary classification. So it's in the context of our course, when we're thinking about the brain, it's a prototypical example of some tasks that our brain needs to do a lot, right? Okay, now a dichotomy is some general function from Rn to 0 and 1, and we're now going to consider a particular architecture for realizing a dichotomy, which is similar to what we did so far, in the sense that it's linear. It's almost linear. It cannot be linear because the output is either 0 or 1. But the idea is that I will show it on a two-dimensional case. So we will look at dichotomies that have the following structure. We pass some line in the two-dimensional case, some line through the origin, and we classify all the points on one side as 1, and all the points from the other side okay, this will be a substitute for red as 0. Okay? So every point on this side will be classified as 1, and every point on this side will be classified as 0. We can formally describe such a function by, first of all, describing this line. Okay, so how can we describe this line? We don't. What do we care about? Yeah, the direction of the line. Now, if we were be in n dimensions, where n is larger than 2, and we want to divide the space into 2 categories, then instead of a line, we'll have a hyperplane, right? An n-1 dimensional hyperplane. And again, we care about the direction of this hyperplane. So a convenient way to characterize it is by describing the direction of a normal to the plane. Okay, so we will define that as some vector w, and all we care about now is just the direction of w. We don't care about the magnitude of w. And then we can formally describe this kind of linear dichotomy by asking, take for any vector x, how are we going to decide whether it's on one side of the plane or the other side of the plane? What mathematically do we need to do? If I give you a vector x, what do I need to do with this vector x to decide whether I'm classifying it as black or red? What is positive or negative? Yeah, okay, so we take the vector, we project it on W, and this gives us a number. And as Peleg said, if this number is positive, we're on one side, and if this number is negative, we're on the other side. So we can, for example, write something like this, but formally, if I write it like this, it means that we're taking a -1 or 1. So you know what? Let's decide that we're mapping not to 0, 1. We're mapping to -1, 1, just for convenience. And then this is a way to write this linear dichotomy. And note that what matters here, indeed, is just the direction of W. Right? Because if we would multiply W by some positive constant, it would not matter at all what is this it would not change this function at all. But the positive constant. So the sign does matter. The sign determines, so W determines both the direction of this plane and which side of it is classified as man and which side of it is classified as -1. If we would switch the sign of W, switch W to -W, will switch the role of the +1 and -1. All right, so this is a way to write a linear dichotomy. And it's probably the most simple mathematical way to realize a dichotomy. But also, another reason why we care about linear dichotomies is that it's a very kind of prototypical, simplified picture of what a neuron does. Okay? A neuron takes its inputs, sums them up linearly, and makes some nonlinear decision based on these inputs. Say whether, in a very idealized manner here, whether to fire or not to fire. Okay? So the fact that we have here a linear function followed by nonlinearity is a very simplified but important model for this ingredient of neural computation in a net, which we might want later to put into a larger, more complicated network. Anyway, so now what I want to discuss is what linear dichotomies can do, what's in the space of all possible dichotomies. And I want to introduce the concept of capacity. Oh, and by the way, this is the linear perceptron. Okay, the linear perceptron realizes a linear dichotomy. Oh, maybe you can't read here. So this is the linear perceptron. And again, graphically, we can kind of describe it in the way that I described the linear perceptron. We have some input units, x1, x2 up to xn. We sum them up linearly with some weights, w1 up to wn. And then here, the difference between what we did in the linear perceptron and the binary perceptron is here there is this sign nonlinearity. Okay. Anyway, so capacity. So I want to somehow quantify how many different dichotomies can be realized by this architecture. And I will start by asking a question, the following question. So how many different dichotomies can be realized by this architecture? I will ask it in a direct way. How many different dichotomies can be realized by this architecture? So, What did you say? Infinite? Is that what you said? Okay, you said it very quietly, so I okay. By the way, now that I printed the picture that I took last week, I would like to ask you to say your name. So Mo. And I need to, now I have the task of identifying you here. Well, most of you sit actually in stereotypical positions, so it helps. Okay, and let's see if I manage to remember names. Okay, so Moore says that the number of dichotomies is infinite, and indeed that's true. And it's clear that if we make any change in the weight, we change the direction of this plane, we're realizing a different dichotomy. Some points which were classified in one way are now make a slant change, classified in a different way. So this question, how many dichotomies can we realize, is not a good question. The answer is trivial. It's infinite. But we can ask a slightly different question. So we can ask this question given that I provide to you a set of points on the plane. Okay? So if we ask what is the dichotomy, what is the linear dichotomy doing on all the points of the plane, there are infinite number of dichotomies that can be realized. But if I give you a set of points on the plane, you can ask now the number of dichotomies becomes meaningful. Why? First of all, for p points, how many dichotomies are there? 2 to the p dichotomies, different dichotomies. And we can ask now how many linear dichotomies there are, okay? Which will tell us of the 2 to the p dichotomies, how many of them can we realize using a linear perceptron. That's a meaningful question. It's a number. Okay. Now, what can it depend on? What can the answer to this question depend on? Still. Right. So the choice of the p points. So in principle, maybe there's no one answer to this question. Indeed, there is no one answer to this question, but usually there is. There is a one answer. So what I will introduce now is the concept of a general position, which is an attribute of the p points. So let me just point out that this may depend on the p points. Yeah. Yeah, it's the number of realizable patterns, realizable dichotomies, or maybe we will care about the fraction of realizable dichotomies. Okay, so I want to define a general position, which is an attribute of p points in the n-dimensional space. You might imagine that since we're generating our answer in the linear perceptron using some linear combination of the inputs, it might matter whether the points that we're looking at have some linear dependencies between them. Okay, and that's what we were going to care about. Now, if I have an n-dimensional space, I know that if I choose more than n examples, they will be linearly dependent. That's for sure, right? So, but I want to define some concept of a set of points which has no linear dependencies beyond what it has to have. If I have more than n examples, they will be linear dependent, but I still want to ask whether there are some less trivial dependencies in them. So a general position, so a set of points x alpha in Rn is said to be at a general position if no set of no subset of less than n, or at most n points of points is linearly dependent. You know what? Why am I writing it with two negatives? I will write it. This is what I have in my notebook. So we can just say that if every subset of m smaller than n points is linearly independent. Okay, so in general, why am I calling it a general position? Because if you imagine that you draw, say, you draw your examples independently from each one of them from some distribution, which is not concentrated on some planes or lines or something like, or hyperplanes. It's a continuous distribution. Then with probability 1, you will get a set of points which is on a general position. The probability that they will happen to have some linear dependencies in that case is essentially 0. So, and the reason that this concept is important is that, as you will see in a moment, if we choose, it turns out that for the linear perceptron, that if we choose a set of points which are on a general position, it doesn't matter for the capacity what they are. Regardless of what exactly the points are, as long as they're in a general position, you'll get the same capacity. And this is a theorem which is called Cover's theorem. But actually, I see that before that, okay, so I need to make a definition. But maybe I will put here first the title, Cover's theorem. That's the same cover that appears on the title of the book that I mentioned on information theory. It's a theorem from 1965. So I will actually, just on the side, write down explicitly something that I said in words, but maybe just to be clear, a dichotomy on p points, which we can describe as the set of x mu, y mu, or x alpha, x mu, y mu, where y mu is now plus minus 1, is said to be linearly separable if there is some w such that y mu is the sign of w x transpose x mu for all the mu's. Okay. Okay, so it in words it means that the dichotomy can be realized by an n-1 dimensional hyperplane through the origin that passes through the origin. Okay, so okay, so now Cover's theorem. The number of linearly separable dichotomies on a set of p points lying in a general position is equal to So this number of linearly separable dichotomies is a function of the dimensionality of the space and a function of the number of points. So that's, and the point is it's just a function of these two. It's as long as the points are in a general position, it doesn't matter what they are. And the number is, which is not obvious, okay? And the number is 2 times sum over k going from 0 to n minus 1, p minus 1 over k. Okay. Now, just as a note in terms of the notation, in terms of the notation, this is like the number of, this is the number of ways to choose k elements out of p minus 1 elements, and you can see here that if n is larger than p, we might have here cases where the number here is larger than the number here. Okay, and we just define this this quantity as 0 in those cases. So now the proof of this theorem we will do with Neta. Not this week, because there will be no TA this week, but you will do it with Neta. I think we'll see. Maybe I will do it. I will decide with Neta, but I'm not going to do it now. I just want to go through some examples now to see that this makes sense. Okay. And also, but before I go through the examples, I want to point out that for the binary perceptron, we could define a similar quantity for other architectures. For the binary perceptron, what is remarkable is that this is not a statistical statement about the average number of dichotomies that can be realized, but it's a precise statement, and because this does not depend on the position of the points. Okay, so let's go through some examples, some simple examples, just to see that it makes sense. Let's take n equal to 2, so we're in the two-dimensional plane. And let's start with p equals 1. So we choose 1 point. How many dichotomies are there on 1 point? 2, because we can classify this point either as 1 or as minus 1. So we expect phi of 1, 2 to be 2. Let's see what this formula tells us. So we have here 2 times k needs to go from 0 to n minus 1. N is 2, so k is going to be 0 or 1. And we have here p minus 1, so p is 1. So we have here 0, 0 plus 0, 1. Right? This is 0 by definition. This is, I actually have to say that this is defined as 1. Okay, so we get here 2, right? 1 plus 0 times 2, so we get here 2. That's fine. Let's take the case where we have 2 examples. P equals 2. So I will add now another example. Right? let's do something like this. Okay. So now, how many dichotomies are there? Name? And good. You're sitting also quite consistently. Okay. Now, why 4? So, first of all, in this example, the plane can be either separating these two examples, right? Or the two examples can be on the same side of the plane. So these are already two choices. Now, if the plane is, say, separating between them, we have to decide which one will be designated as 1 and which one will be designated as 1 minus 1. So it's two possibilities. And also, if the plane is not separating them, we have to decide whether they will be both of these examples will be classified as 1 or as minus 1. So we expect to see 4. Now let's just do the calculation, which we're just calculate this expression. So now it's p minus 1 is now 1. So it's going to be 1 over 0 plus 1 over 1. This is 1, this is 1, so we have 2 times 2, and we have 4. Let's do one more example with 3 points. So p is equal to 3. What's the situation now? How many dichotomies? 8. So there are 8 possible dichotomies, but the question is how many linearly separable dichotomies there are. So I claim it's not 8. Okay, so we need to first choose the direction of the plane, and you can see here that there are 3 possibilities. Each one of the points might be on one side of the plane, and the 2 other points might be on the other side. I could have drawn a different set of points. For example, if I would put the orange point here, we could have also a possibility where all the 3 points are together, right? So there are different scenarios, but all of them will yield the same capacity. So, or the same number of realizable linear dichotomies. So, but in this case, if the orange point is here, we'll always have 1 point on one side of the plane and 2 points on the other side of the plane. And there are 3 ways to do that, right? To choose which point will be special, will be on the alone. And then we have to decide which side is 1 and which side is minus 1. So we expect how many linearly separable dichotomies? 6. Okay, so let's just write down. Here we'll have 2 over 0 plus 2 over 1. That's the expression written here. This is still 1. This is 2. 2 times 1 plus 2 is 6. Okay, so it works correctly for the examples that we checked. And the proof, as I said, I'm not going to do today. What I do want to do is to understand a little bit better now what this expression is telling us. So I want to understand something about the behavior of this expression. So, behavior of Cpn as a function of n, as a function of p. So let's start with small number of examples of points, and as you'll see, the relevant we will be able to say something special about the case where p is smaller than n. And the reason why p smaller than up to n is special is that as long as p is smaller or equal to n, we don't encounter in the sum these cases where we have here something here something larger than here, right? So all the terms here are terms where this is smaller than this. So if p is smaller than n, c of p of n is equal to sum. I just write it again. A sum, 2 times sum over k going from 0 to n minus 1 p minus 1 over k. And I claim that this is really equal to the following. Oh, sorry. So here, sorry, it's the opposite of what I said. If p is smaller than n, then at some point where we're going over the sum, when k will reach p, it's exactly the opposite of what I said. I was confused. When k reaches p, then we will have here k. When k reaches p minus 1, we'll have here this equal to this, and then the rest of the terms will be 0. Right? You're with me? And therefore, when I write this sum, I can replace n by p. Okay? So I go through all the terms which are not 0 here, and all the rest of the terms are 0. And now this, I claim, is just this, right? Because when you write down the binomial coefficient, when you write down a sum of 2 terms to some power and you express it as a sum of powers, this one and this one with some coefficients, these are exactly the binomial coefficients, right? I mean, you can write in general. Is this clear, or do I need to explain? Is it clear to everyone why this is true?
What did you replace?
So, okay. So first of all, what I did is I replaced n by p here. So the sum here goes up to n. But the point is that n is larger than p, and all the terms where k is larger than p minus 1 are 0. And now my question is whether this equality needs some explanation. Okay, thank you. So if we write down a plus b to some power n, we can break it up to a sum where k goes from 0 to n of, the idea is, what is that? This is a plus b times a plus b times a plus b and times, right? So all the terms that I get will be some power of a times some power of b. In each one of these expressions, I need to choose either a or b. And so what matters is how many times I chose a, how many times I chose b. So k will be, say, the number of times I chose a. So I'll have a to the power of k, and in any time that I didn't choose a, I have Bn minus k times. And then there is some coefficient here. The coefficient here is the number of ways to choose k elements out of n, which is n over k. Okay? Now, if we take the example where a and b are 1, and n is now p minus 1, you can see that this equality holds. Okay? So, if that's the case, what does that mean? It means that what we got here is 2 to the power p. What does that mean? Thank you, Hadass. It's very helpful. All the dichotomies are linearly separable. Okay. So this is p smaller than n. It makes sense that as we add more and more points, it might become more difficult to, at some point we might reach a situation where we're not realizing all the dichotomies. We saw that in this example, right? When p was equal to 1, we realized both of the dichotomies. When p is equal to 2, we realized all the 4 dichotomies. When p was equal to 3, we did not realize all the 8 dichotomies. We only realized 6 of them. So I want to check a particular case which is easy to deal with, and this is the case of p equals to 2n. Because it turns out that for that case we can write down a simple expression. We can simplify the expression that we have here. So when p is equal to 2n, then Cpn is equal to 2 times sum over k going from 0 to 2n minus 1. Sorry, n minus 1. And here we're going to have 2n minus 1 over k. So now I'm going all the way up to n minus 1, whereas here I stopped at p minus 1. Now all of them, I go through all of them. I never reach the situation where one of these terms is 0. And but in the special case where it's here it's n and here it's 2n, because p was equal to 2n, there is something neat that I can do with this sum. And so the idea is that here in this sum we have here n terms where k goes from 0 up to n minus 1, right? And now what I claim that I can add another n terms and complete this sum. Instead of going up to n minus 1, go up to 2n minus 1. So I will write something. I will justify it in a moment. What I'm going to do here is I'm going to sum these kind of terms where instead of going from k to n minus 1, I'm going to go to 2n minus 1. Okay? So I added another n terms. But I claim that the n terms that I added here are exactly equal to the n terms that I had before, because now I have here 2 n terms. K goes from 0 to n minus 1, and then n up to 2n minus 1. And I claim that every term here has a term here which is exactly equal to it. Because 2n minus 1 over k is also the same as 2n minus 1 over 2n minus 1 minus k. So this term is equal to this term, and then this term will be equal to this term, and then this term will be equal to this term. So all this sum is exactly the same as this one except for a factor of 2. So I can write here a 2 that we had before, but add a half because I just have now, I doubled the terms. Okay? Therefore, this is already a familiar object. What is that?
This is the power of 2n minus 1.
Yeah. So I have here 2 times half times 2 to the power of 2n minus 1. In other words, what I got is 2 to the power 2n minus 1. What does that mean? How many realizable patterns are there? Sorry, how many patterns